Question 4. A sample of titanium was ionized by electron impact in a time-of-flight mass spectrometer. Information from the mass spectrum about the isotopes of titanium in the sample shown in Table 2. So mass divided by Z, that's mass divided by the charge on the atoms, or the ions now. So the atoms are ionized and they lose one electron, so they become +1 charge. So mass divided by +1, mass divided by 1 is just the mass. So these are the masses of the atoms in titanium. Why does titanium have atoms of different mass? Well, they're all titanium because they've all got the same atomic number or proton number. They've all got the same number of protons and electrons, but they've got different numbers of neutrons, and that's why they have different masses. They're called isotopes. And this is the percentage abundance. So 9.1% have got mass 46, 7.8% have got mass 47, 74.6 have got mass 48, and 8.5% have got mass 49. So if you imagine you had 100 particles, 9.1 out of the 100 have mass 46. So their combined mass is 9.1 times 46, 418.6. And you can do the same for the others. 7.8 out of the 100 have mass 47, so their combined mass is 366.6. 74.6 out of the 100 have mass 48, so their combined mass is 3580.8. And 8.5 out of the 100 have mass 49, so 8.5 times 49 is 416.5. So the total mass, if you add them all up, the total mass of all of the 100 particles altogether is 4782.5. The average is the total mass, 4782.5, divided by the number of particles, divided by 100, is 47.8. It requests it to 1 decimal place, and we've given it to 1 decimal place, 47.8. So, write an equation including state symbols to show how an atom of titanium is ionized. So you've got Ti, and it's a gas. It's got to be a gas. So going into the time-of-flight mass spectrometer, it's a gas, and then an electron is removed from it, so it becomes Ti+. Again, it's still a gas. So including state symbols, they're all gases. MZ value of the ion that would reach the detector first. So the one that's going fastest would reach the detector first. The one that's going fastest has got the smallest mass. So 46, titanium with a mass of 46, that atom would reach the detector first. 49 would reach it last because that's the heaviest. Calculate the mass in kilogram of one atom of titanium. And you give them the Avogadro's constant. So the average mass of 1 mole would now work as 47.8. We know the number of particles in a mole is 6.022 times 10 to the power 23. So it's 0.047 kilograms. So to convert grams into kilograms, you divide by 1,000. So a small unit going into a larger unit, divide by 1,000. So it's 0.047 kilograms. It requests in kilograms, divided by the number of particles in there, will give you the mass of 1 particle in kilograms. In a time-of-flight mass spectrometer, the time-of-flight T is given by this equation, where D is the length of the flight tube, M is the mass of the particle in kilograms going down the tube, and E is the kinetic energy of the ions. So the things that aren't going to change, the distance, though the length of the tube is not going to change, so D is going to stay the same, and E, the kinetic energy of the ions. The kinetic energy of the ions put into the tube is always the same, irrespective of what kind of ion you put in there. So E is going to stay the same, so 2 lots of E are going to stay the same. So D and 2 lots of E are all going to stay the same for each of the ions that are put in there. So we've said that already. So I've rearranged this equation. I've taken square root of m divided by 2e. From the top on this side, I've taken it across the equal sign, it goes onto the bottom. So d is 2 divided by the square root of m over 2e. And so the distance, or the length of the tube, is going to be the same. So this value, t divided by the square root of m over 2e, is going to be the same for whichever ion you've got. So for 49 titanium Ti, and 47 titanium Ti, then T divided by square root of m over 2e is the same for each. And I've even cancelled 2e as the same on each side as well. So 2e is going to be the same on this side. So T divided by square root of m over 2e is the same as T divided by m over the square root of m over 2e on the right hand side. I've cancelled the 2e on each side because 2 lots of E, 2 lots of the kinetic energy are the same for each particle. So now I've got the time divided by the square root of the mass of the particle equals the time for this to reach the detector, 47 Ti, divided by the mass of this one. The masses are 49 and 47 respectively, so T divided by the square root of 49 equals T divided by the square root of 47. The times are different, of course. The time for 49 Ti is given as this value here, so 9.816 times 10 to the minus 7 divided by the square root of the mass of the particle 49 is time taken for the 47 Ti to hit the end of the tube, the detector at the end of the tube, divided by its square root of its mass, 47. So I've multiplied both sides by square root 47, and so T, the time for 47 Ti, equals 9.612 times 10 to the minus 7.